Hello. Today I'm going to be presenting random phase approximation for cold atomic gases. Here's my abstract. The general purpose of statistical physics is to explain how the collective macroscopic properties of systems in nature arise from the microscopic interactions of their constituent atoms and molecules. Accounting for all the interactions in a classical system is quite challenging. In a quantum system, we have the added difficulty that particles behave in fundamentally different ways from classical objects. In the quantum realm, our everyday intuitions about how an object should behave provide us with little guidance. Despite these problems, theorists and computational physicists have risen to the challenge of quantum many-body physics and developed many ingenious theoretical and simulation-based techniques to address them. One approach is random phase approximation, powerful theoretical formalism that has been successfully applied to study superconductors, cold atomic gases, and other exotic quantum systems. In this talk, we provide an intuitive overview of RPA applied to cold atomic gases and give our preliminary results for the collective density fluctuations of the system calculated using RPA. Intriguingly, by solving the properties of cold atoms, we may also uncover information about the properties of seemingly disparate systems, such as superconductors and neutron stars. By exploiting this fact, we may be able to partially solve multiple problems in quantum many-body physics at once. So here's my outline of my talk. I'm going to briefly overview cold atomic systems, the Hubbard model Hamiltonian, static correlation functions, the dynamical structure factor, and I'll also talk a little bit about quantum Monte Carlo and also our random phase approximation results for the dynamical structure factor. And then I'll talk a little bit about where we might like to go with our research. So cold atomic gases are collections of large numbers of bosons or fermions cooled to low temperatures. We cannot easily access the insides of exotic systems such as superconductors or neutron stars. Realized either in the lab or with computer simulations, cold atoms provide an avenue for studying quantum many-body systems. We may be able to simulate the behavior of an inaccessible system, such as the superfluid interior of a neutron star, with a more manageable cold atomic gas. We may also be able to study exotic phases of matter where intuitions about solidity and fluidity overlap, such as the supersolid phase. So experimentalists can prepare cold atomic gases by combining and organizing clouds of cooled lithium or potassium atoms with interfering laser beams and cooling them to the microkelvin to nanokelvin range. It is also possible to embed the gases in an external field. By doing this, one can create an optical lattice where atoms are constrained to spend most of their time at a discrete set of points in space. We use computer simulations to study a spin-balanced cold atomic gas of fermions on a 2D optical lattice at half filling. In this regime, the system organizes into a supersolid phase, a superfluid with a checkerboard density modulation. So I'm going to talk about the Hubbard model Hamiltonian. We modeled the system using the Hubbard model. Though the model is relatively simple, no analytical solutions exist. We studied the attractive case, where this parameter U, which is related to the potential energy, is negative. So the kinetic energy part is responsible for modeling the motion of particles as they hop from one site in the optical lattice to another. The potential energy part allows for particles with opposite spins to interact, bind, and form pairs. Two particles with the same spin cannot exist on the same lattice site. This follows from the Pauli exclusion principle. It's indicated there. So now I'm going to go into a little bit about our results. So this is just an introduction to correlation functions. Correlation functions, these are a very broad class of functions that tell us how one property of a system is influenced by another. An example of a spatial correlation function for a classical system is G of R, which tells us the likelihood of finding particle distance R from a reference particle. It's also called the radial distribution function. An example of a time correlation function is the velocity autocorrelation function, which tells us how the velocity of the ith particle in a system at time t depends on its velocity at time 0. And here's just a little plot from a molecular dynamics simulation I did of a Lennard-Jones fluid for the velocity autocorrelation function. So now here are results for super solid quantum system we were studying. So this is the density correlation. So if you imagine sitting on a particular particle, the density correlation is the probability of observing another particle a distance r away from you. At half filling, the system organizes into a structure with a periodic density modulation. You can see that here. This is a characteristic property of a solid. We stress that this periodicity is completely different from the periodic structure of the optical lattice. This is something that emerges from the quantum nature of the system and the physics involved. So now we have the pairing correlation. A spin-up particle and a spin-down particle can meet at a lattice site, bind and form a pair. Pairing correlation is proportional to the probability of finding a pair traveling a distance r from the site where it initially formed. Notice that the function goes to a small non-zero value of r as r becomes, the absolute value of r becomes large. You can see that here. There's this gap. This tells us that the particles and the pairs they form are quite mobile within the system, a characteristic property of a superfluid. This property, combined with the density modulation mentioned earlier, confirms that we have indeed found a supersolid on the lattice. So now we have the main result, the dynamical structure factor, which is defined here. Figures give our results for the dynamical structure factor. This function gives the distribution of possible exchange momenta and energy between the system and a probe. Intuitively, it measures the probability of the system's momentum changing by q units and the energy changing by omega units after being probed. The high peak at m equals a pi, this momentum here, indicates the system is a solid because it causes zero energy, it's on the zero line for omega, to impose that density modulation on it. Essentially, the system already has that periodic structure as its preferred state. So it already wants to be there, so it doesn't cost any energy to put it there. Static properties have been calculated before for the system, but these results for the dynamical properties are new. And here's our results using GRPA, or random phase approximation, and here's also quantum Monte Carlo. So that, like I said, GRPA is generally considered the standard method for performing these kinds of calculations. And the reason is we can achieve much higher resolution in the momentum and energy domains, though the results are not unbiased. So GRPA is based on approximations, whereas QMC is exact, but QMC is much, much more computationally difficult to do. Yes, so the bottom figure is a result for dynamical structure factor obtained using quantum Monte Carlo, and we also have to do analytic continuation. And we can only do, stretching it about for a 12 by 12 lattice. So given the close agreement between our results, QMC may serve as a useful benchmark to assess the quality of results from GRPA. That's what we're hoping. So in the future, hopefully the fairly near-term future, well, we are calculating the response functions and implementing the code needed to perform GRPA for the spin dynamical structure factor. We also want to perform QMC and GRPA calculations for a dilute system on an optical lattice, where all the sites are not occupied. Longer term, we are interested in spin-orbit coupling, where particles can flip their spins as they move through the lattice. Using QMC, GRPA, or both, we would like to calculate the viscosity of these exotic systems, though that's probably going to be a little bit harder to do. We're also hoping that our research should guide experimentalists through some of the difficulties that come with creating exotic phases, such as the supersolid in the lab. And that's my talk. Thank you. Have a nice day.